In this video, we're going to talk about linear functions and their properties. One form linear functions take is f of x equals mx plus b, which is the slope-intercept form, where m represents the slope of the line and b represents the y-coordinate of the y-intercept. And as a quick reminder how to graph a linear function in mx plus b form, let's take an example. So let's say that we have this function here, f of x is equal to negative 3x plus 7. You start with that 7, or that b value, your y-intercept, and you'll plot it there. And then whatever your slope happens to be, so our m, or our slope, is negative 3. So if you remember that as like rise over run, or change in y over change in x. So that means that I'm going to drop down 3 and go over 1, because this is like negative 3 over 1. Drop down 3, go over 1, drop down 3, go over 1, etc. Another way to think about slope is to think of it as an average rate of change. So for a linear function, its average rate of change, its change in y over change in x, is constant. So the slope at one point on a line is the same at every other point on that same line. And whether or not you need to determine the slope, determine if it's a linear function with a constant average rate of change or a constant slope, you can take whatever data that you have and figure out what that slope is. So if you had the graph, and let's say you didn't have the function, so you don't know what m or b would be, you could take 2 points, preferably more than 2, but since we have 2 here. And let's say that we have these 2 points, 0, 7, 1, 4. We're looking for the change in y over change in x, so we're looking at the y values first. So to go from 7 to 4, you have to drop 3, it goes down by negative 3. And to go from 0 to 1, well, that's up by 1. So negative 3 over 1, negative 3. Same kind of idea on a table of values. So if you had an xy table and you didn't have the function and you need to identify whether it's linear or what the slope is, you could do the same thing that we did over here. So the change in y over change in x. So in order to go from 13 to 10, you drop by 3, so that's the negative 3. And to go from negative 2 to negative 1, that's going to be a positive 1. Negative 3 over positive 1, negative 3. And again, you would want to check more than one pair of points to determine if it's a linear function. But if you're just looking for the slope and you knew it was a line, you could just take any 2 points. Now let's take a look at 2 real-world examples and see if data collection tables represent a linear function or a nonlinear function. This data table represents a strain of E. coli and its population on a petri dish over a certain number of hours. Delightful. So what we're going to do is we are going to find the change in y over change in x between at least 3 points. So the first set of data points is time 0, time 1 hour, and that slope is going to be 0.03, because from 0.09 to 0.12, 0.03. Great. And that is going to be from 0 to 1, so that's over 1 hour. In fact, everything here is by 1, so that makes finding the slope so easy, or the average rate of change, so easy. But I run into a problem immediately, because to go from 0.12 to 0.16, that is a change of not 0.03, but 0.04. So already I know that this is nonlinear. But as I carry through, all of the change in y over change in x is very different. So this represents a nonlinear function. Another way to analyze if this data set is linear or nonlinear is to graph the points as they are. So maybe between the first 2 points you could create a line there, maybe, but as you keep going, it definitely creates a curve, which is obviously nonlinear. And our second data table here represents the maximum number of heartbeats that a healthy individual should have during a 15-second interval of time while exercising for different ages. So our x is our age, and y is our maximum number of heartbeats. So I'm going to do the same thing and analyze delta y over delta x and see if we have a linear or nonlinear function. All of my delta y's in this set are a negative 2.5, and all of my delta x's are a positive 10. So negative 2.5 divided by 10 is negative 0.25, which would be the slope for this linear data set. And visually, we can also confirm that this is going to be linear because we have the same slope between all of the points, which makes it linear. Gotta love when that works out. Another thing you can do with linear functions is determine whether or not it is an increasing, decreasing, or constant linear function. And you do that by analyzing the slope. So let's take a look at these 4 examples and figure out, are these increasing, decreasing, or constant? So each of these functions is in mx plus b format, which makes it wicked easy to find our slope or our m value. So we look for whatever our input is. So if I have f of x, that means that x is my input or my independent variable, and whatever number is right in front of it is my slope. So in A, my variable is x, number in front is 5, so that means my slope is 5. It's positive, therefore it's increasing. Also in B, my input is x, my m value, my slope is negative 2, and that means that I have a decreasing function or slope because the slope is negative. And then in part C, I have an input of t. That's not a problem. 3/4 is going to be my slope. That's positive, so it's increasing. And then D, my input is z, and all I have is a 7. So all that means is that my function is a horizontal line that crosses through y equals 7, which means that I have a 0 slope. Not no slope, which is different. So if my slope is 0, that just means that I have a constant function. Now let's take a look at one last multi-part example of supply and demand. Good old economics crash course here. So a couple of things to identify. One is quantity supplied is the amount of the product that a company is willing to supply, and quantity demanded is what people want to buy from this company. So let's say that the quantity supplied S of P is and the quantity demanded D of P of cellular telephones, cell phones, y'all, each month are given by the following functions, where P is the price in dollars of the telephone. The first thing that we are asked to find is the equilibrium price, which is the quantity supplied, our S of P, that is equal to the quantity demanded, our D of P. So we're going to find the P, or the price in dollars of the telephone, and then we will use that to find the equilibrium quantity, which is the amount demanded or supplied at the equilibrium price. So when I set these two equal to each other, I do some algebra, and I find that the price is $50 per telephone. So in order to find the equilibrium quantity, you can plug it into either equation, because remember, they're the same value at this price. So S of 50 or D of 50 is going to give you 2,100 telephones. Next, we're being tasked to determine the prices for which quantity supplied is greater than quantity demanded. So if this is quantity supplied and this is quantity demanded, we set this one greater than this one. And let's see what the price is. So essentially, it's the same equation as the last slide, except we're working with an inequality symbol. So I'm going to do the same algebra to find that P is greater than 50, which should make sense, which means that at greater than $50, so if you charge more than $50 per phone, then the quantity supplied is going to be greater than the quantity demanded. The last thing to do here is to graph both equations and figure out the equilibrium point. So we determined that at $50 and 2,100 phones supplied is the sweet point, the equilibrium point, where these two things equal each other. So while graphing these two lines is all well and good, being able to analyze this graph is far more useful. So on the left side of this equilibrium point, you see that this equation, D, or D of P, which is the quantity demanded, is higher or greater, has a greater Y values than our S or S of P, which is quantity supplied. So that means that the demand is greater when your cost per phone is less than $50, but then the opposite is true, past $50. So when you charge more than $50 per phone, the quantity supplied goes up and the quantity demanded is less after $50. And that's going to do it for this video. Thanks for watching.